By 2026, 3 Pentagon programs leave the lab and enter operational deployment. Not concept art, not speculation. These are funded programs with defined engineering milestones: autonomous mass, hypersonic kinetics, and field-grade directed energy. Today, we examine what is actually crossing the prototype gap, the specific systems architecture that will define the American way of war for the next decade. In high-end conflict, the side that masters the transition from lab to theater wins. We begin with the Replicator initiative, a fundamental shift in force design. Chapter 1. Mass Autonomy, Replicator. For decades, U.S. force design emphasized a philosophy built around fewer, highly capable platforms, advanced aircraft, capital ships, and precision weapons that delivered overwhelming capability through technological superiority. But modern conflict is revealing a different equation. Scale is returning as a decisive variable. The Pentagon's Replicator initiative represents a structural shift toward distributed autonomy. Thousands of lower-cost systems designed to operate collectively rather than individually. But scale alone isn't the breakthrough. The real question is how thousands of machines think together. The goal is not simply to deploy more drones. It is to deploy autonomous networks capable of functioning as a coordinated system under contested conditions. At the heart of this architecture is the problem of coordinated logic. Individual drones are relatively simple machines. The real engineering challenge lies in enabling them to make decisions locally while remaining synchronized with the broader mission. And that coordination becomes critical the moment communications start to fail. In electronic warfare environments where satellite links may be jammed and communications degraded, centralized control becomes fragile. Distributed autonomy solves this by embedding decision loops directly within the network itself. Each unit processes sensor data locally, shares minimal mission-critical information with nearby nodes, and collectively maintains operational cohesion. The milestone expected by 2026 is mission-level objective execution. Swarms capable of conducting surveillance, electronic attack, or strike coordination without continuous human supervision. At that point, autonomy stops being a tool and starts becoming a force multiplier. This approach fundamentally changes force design. Instead of protecting a handful of exquisite platforms, commanders deploy resilient networks where losing individual nodes does not compromise the mission. In this model, resilience comes from redundancy and adaptability rather than perfection. The Replicator initiative therefore represents more than a new drone program. It represents a shift in the logic of military scale. Chapter 2. Hypersonic Kinetics, Dark Eagle. Parallel to the rise of autonomy is another transformation driven by physics: time compression. Hypersonic weapons operate at speeds exceeding Mach 5, where the dynamics of flight fundamentally change. The U.S. Army's long-range hypersonic program, often referred to as Dark Eagle, is designed to exploit this regime of extreme velocity. But speed at this level introduces physics problems most missiles never face. At these speeds, traditional assumptions about aerodynamics and guidance begin to break down. As the vehicle accelerates through the upper atmosphere, friction generates intense heat and ionizes surrounding air, forming a plasma sheath around the vehicle. This plasma layer can interfere with radio frequency signals, a phenomenon known as plasma attenuation. In practical terms, the weapon may temporarily lose the ability to receive guidance updates or transmit telemetry while traveling at peak velocity. And that communication blackout becomes one of the hardest engineering challenges in hypersonic design. This creates a significant engineering challenge for precision strike systems that must travel thousands of kilometers while remaining controllable during the terminal phase of flight. The milestone expected by 2026 focuses on aero-thermal management, engineering solutions that control heat loads while preserving maneuver authority. Advanced materials, thermal protection layers, and adaptive guidance algorithms work together to maintain stability during hypersonic flight. Because at Mach 5 and beyond, survival is just as important as speed. The objective is not simply speed, but controlled speed. A vehicle capable of surviving extreme heat, adjusting trajectory, and striking with high accuracy despite the complex physics surrounding it. In strategic terms, hypersonic systems compress decision timelines for adversaries, reducing reaction windows from minutes to seconds. This speed advantage alters deterrence calculations and complicates traditional missile defense architectures, forcing military planners to rethink how interception and early warning operate in an era defined by extreme velocity. Chapter 3. Directed Energy, the Cost Curve. While autonomy and hypersonics change the geometry and speed of warfare, directed energy systems transform its economics. High-energy lasers are moving from experimental demonstrations toward operational integration across multiple military platforms. Unlike traditional interceptor missiles, which require expensive propulsion systems and complex guidance packages, laser weapons deliver energy directly to a target through a focused beam of light. But the real breakthrough is not the laser beam. It is the economics behind it. The primary engineering constraint is no longer generating the beam itself. Modern solid-state lasers can achieve impressive power levels. Instead, the limiting factor is power density, the ability to sustain high output without damaging the system that produces it. A laser operating in the 300 kilowatt class generates immense heat during firing. And managing that heat is what separates a laboratory experiment from a battlefield weapon. Without efficient cooling mechanisms, internal components would degrade or fail after only brief use. The 2026 milestone therefore centers on modular thermal dissipation systems, closed-loop cooling architectures that circulate liquid through high-temperature components, rapidly removing excess heat and enabling sustained firing cycles. This technological shift allows lasers to move from short bursts to operational duty cycles suitable for air defense or counter-drone missions. Once that barrier is solved, the economics of defense begin to change dramatically. The strategic implication lies in the cost curve. A traditional interceptor missile can cost hundreds of thousands or even millions of dollars per launch. In contrast, the marginal cost of firing a laser shot is largely determined by the electrical energy required to power it. Although the initial platform investment remains substantial, the cost per engagement drops dramatically over time. In environments where adversaries deploy large numbers of low-cost drones or missiles, this economic advantage becomes decisive, favoring the side capable of sustaining defensive fire without exhausting expensive inventories. The adaptive systems architecture. The significance of 2026 is not defined by a single breakthrough, but by the convergence of multiple technologies into one operational architecture. Mass autonomy introduces scale, thousands of distributed systems sensing and acting across large theaters. Hypersonic weapons compress time, forcing decisions in seconds rather than minutes. Directed energy changes the economics of defense by reducing the cost of interception. Individually, each capability is powerful, but the real transformation happens when they operate together. Autonomous networks expand situational awareness. Hypersonic strike systems exploit that awareness with extreme speed. Directed energy platforms sustain defense against large volumes of threats. Warfare becomes less about platforms and more about architecture. If you want the next briefing on undersea autonomous systems operating across the Pacific Theater, comment Pacific below. Subscribe for the next deep dive. Dismissed.